Hi, everyone. So today we're going to be talking about ionic and net ionic chemical equations. So you already know how to write a molecular version of a chemical equation. This is when we just show the full formula of everything. Now, when we have something like an ionic chemical equation, we're going to show the aqueous substances as ions. And I'll show you what I mean in a second. This makes more sense when we do examples. And then we show solids, liquids, and gases as compounds because they don't break apart in solution. So what aqueous means is that an ionic substance that is soluble. So something like sodium chloride, that's an ionic substance. We know that when we put salt in water, that Na and Cl are going to break apart. So this is what aqueous means. It means that that substance, NaCl, sodium chloride, this breaks apart in water, and so it exists as Na plus and Cl minus instead of together as NaCl. So solids, liquids, and gases, however, they're not going to exist as those individual ions like sodium chloride will. So that's why we don't call them aqueous. We just write them as S, L, or G when we're writing our chemical reactions. And then our net ionic equation, we eliminate spectator ions. Again, this makes more sense when we actually do an example. So let's do an example. I have this reaction here. I have potassium chromate plus barium chloride, and then this is a double replacement reaction. It reacts to form potassium chloride and barium chromate. We can see that we have some subscripts here that the two reactants and then the first product, those are all aqueous substances, but then that barium chromate is a solid. So there are some ionic substances that are not soluble. If you mix these two things together, these two reactants are potassium chromate and barium chloride, you would get what's called a precipitate in solution. And basically, what would happen is that barium chromate is going to come out of solution as a solid. So that's the insoluble thing, that barium chromate. So, this is my molecular formula, chemical equation. And then what we want to do here is we want to now write my ionic and my net ionic equation. So, what I'm going to do for the ionic equation is I'm going to split all the aqueous substances up into their ions. So, everything that's labeled with an AQ, we split up into ions. So, I split up that potassium chromate. Notice how the subscript on the potassium, that 2 right here, right? That becomes a coefficient because I have two potassium ions. That's how you would kind of read that. And then the chromate, I only have one of those, and I keep it together because it's a polyatomic ion. So I have CrO4 minus 2, that's the charge. You want to make sure that you're writing your charges here because when we split these things up, they are charged. If I don't put the charge on the potassium there, it's not a potassium ion anymore. It's just a potassium atom. So those things are different. So you really, really need to put your charges when you're writing an ionic formula. And then my barium chloride, I know that barium is a positive 2 charge, and then my chlorine is a negative 1 charge when it becomes the chloride ion. Again, I have 2 chlorides to balance out that positive 2 charge on the barium. So I put that 2 in front because, again, I have 2 chloride ions. I don't have Cl2, right? Chlorine gas is Cl2. That's going to be different. It's not charged. It's not just 2 ions. It's chlorine gas. So this is very different. You have to write it like this when you're writing your ionic chemical form equation. Again, potassium chloride, I'm going to split that up into potassium. This is a typo, of course. I haven't fixed it yet. This should be just +1, right? Because a potassium is an alkali metal, that first group. It becomes a +1 charge when it becomes an ion. And then I have 2 chlorines right here. And then my barium chromate, I'm going to leave as is because it's not aqueous. So it's not going to split up in solution. It's going to be a solid in my solution. The next step is I want to make my net ionic reaction. So in this step, I'm going to get rid of my spectator ions. So that is going to be substances that are on the same side. That are on the same on both my reactant side and my product side. So in this case, I have 2 potassium ions over here on my reactant side, and I have 2 potassiums over here on my product side, so those cancel out. I have 2 chloride ions on the reactant side. I have 2 chloride ions on the product side. Those also cancel out. But look, I have a chromate ion and I have a barium ion, but I don't have those over here. So those are going to be what is left in my net ionic equation. And so here's what this is. Molecular is at the top, my ionic equation is in the middle, and my net ionic equation is last. So here's another example. We would first have to balance this in order to write our molecular equation. So I can see that I have 1 magnesium over here. I have 1 over here. That's balanced. I have 1 hydrogen over here, but 2 over on the product side. So I would have to put a 2 in front of this hydrochloric acid. And then that gives me 2 chlorines, and I have 2 chlorines there. So that's the only one that I have to balance here, is I have to put a 2 in front of my hydrochloric acid. So this is my molecular chemical reaction. Now, next, I want to write my ionic equation. So I need to take anything that's labeled with AQ, my aqueous substances, and I need to break them up into their ions. So in order to do this, I can see that my hydrochloric acid is aqueous, and also my magnesium chloride is aqueous. My magnesium on the reactant side, that's a solid, so I don't do anything to that. And then also my hydrogen on the product side, that's a gas, so that is not going to be split up either. So this becomes magnesium solid plus 2 hydrogen ions plus 2 chloride ions. Notice how that 2 distributes to both the hydrogen and the chlorine. Remember, the 2 applies to both, so we have to give a coefficient of 2 to both those ions. And then I split up my magnesium ion, which it's an alkaline earth metal, so that's a positive 2 charge. It's going to lose 2 electrons when it becomes an ion. And then plus 2 chloride ions, again, that subscript becomes a coefficient because I'm saying that I have 2 of those Cl minus 1 ions. And then last but not least, I just keep my H2 gas as is. So remember, with our net ionic equation, we now want to eliminate spectator ions. So this is going to be anything that is both on the reactant side and the product side. So I can see that here, the only thing that is on both the reactants and the products is my chloride ion. Notice how I have 2 chloride ions over here and I have 2 chloride ions over here. A lot of people look at this problem and they want to eliminate magnesium, but look, it's not the same. I have a magnesium solid on the reactant side and I have a magnesium ion on the product side. Not the same thing. They do not cancel out. Also, I have 2 hydrogen ions on the reactant side and I have an H2 gas on the product side. Again, not the same thing. They do not cancel out. So the only thing that cancels out here is my 2 chloride ions. And this is my net ionic equation. Now, with these problems, we can also just not give you those subscripts. So like the AQ, the S, the G, the L for liquid, sometimes those are not given, and this is where solubility rules come in. So solubility rules are going to determine whether or not something is a solid in an equation. So if it's insoluble, it's going to be a solid, like that barium chromate example in my first example. That is something that's insoluble, so you would have to write S next to it. What we're going to do is I linked the solubility table on Canvas, so you have to use that table to determine the solubility of compounds when writing chemical equations or reactions. I will give you this table on a test. I don't expect you to memorize it. I don't even have it memorized. Okay. So I will give it to you on a test. You can use it during your homework and stuff like that. Again, I do not expect you to memorize it. So if the thing is soluble, you're going to write this as AQ, aqueous, in your chemical equations. If it's insoluble, you'll write it as S. So like that barium chromate, it was insoluble. It was a solid. It precipitated out of the reaction. Okay, so how do we apply these rules? So example number 3. Here's our example. We first have to balance this for our molecular reaction. And then what we're going to do is we're going to look up these things one by one to see whether or not they are soluble. So balancing here, I have one iron over here, one iron over here. Irons are good. I have two chlorines over here. I have only one over here. So I'm going to need to put a 2 in front of the sodium chloride. I have two sodiums now and only one sodium right there. So I'm going to have to put a 2 in front of this sodium hydroxide. And then that'll give me two hydroxides and two hydroxides. So 2 goes here, 2 goes here. Now, with our solubility rules, we're going to take these one by one and we look them up on the table. So let's start with iron 2 chloride here. Our solubility table looks like this. Let me move myself up here. So this is what our solubility table looks like. Again, we're looking at iron 2 chloride first. Now you see rule number 3 says chlorides, bromides, and iodides are generally soluble. So generally, chlorides are soluble. However, the halides of silver, mercury, lead, and then also these things are insoluble because they're exceptions. Now I'm looking at iron 2 chloride here. Iron is not an exception, which means that this is going to be soluble. So for the first part here, we look up our solubility rules to determine which substances are aqueous and which are solids. Because iron 2 chloride is soluble, we would write AQ next to it for aqueous, all right, because it's going to break apart into solution. Now let's look at sodium hydroxide next. So my sodium hydroxide, hydroxides, let's look for hydroxides. Hydroxides are generally insoluble. However, the exception here, those of the alkali metals. So if you remember, or if you have a periodic table in front of you, sodium is in that first group, it is an alkali metal. So that means that sodium hydroxide is soluble. So because of that, we then are going to put an AQ next to our sodium hydroxide. All right, so you can see part B, we write the ionic and net ionic. We'll do that next. Just hold that thought. So AQ next to this one, AQ next to this one. All right, and then we want to look at iron 2 hydroxide. Again, my iron 2 hydroxide, hydroxides are generally insoluble. Iron is not an exception here. Okay, so since iron is not an exception, that means that we are going to write an S next to the iron 2 hydroxide because it is insoluble in solution. Okay, and then last but not least, we have sodium chloride. Of course, we already know that sodium chloride is soluble because it's just table salt. But let's look at our chlorides again. Chlorides, bromides, and iodides are generally soluble, and then sodium is not an exception here. So we would put an AQ next to the sodium chloride. Okay. Now, after you have all your subscripts, you're then going to write the ionic and net ionic equations for the reaction. So here's our molecular with our AQs and our S's. So remember, this one was soluble, this one was soluble, this one was soluble. Our iron 2 hydroxide was the thing that was insoluble. So we put a S for solid next to it. Next thing we're going to do is we're going to split up those aqueous things. So everything that has the AQ next to it gets split up into solution because, again, they are soluble. Remember, you have to put your charges here. And then if you have any subscripts or any coefficients, those also go along with your ions. So I have the iron 2 plus ion plus 2 chloride ions plus 2 sodium ions plus 2 hydroxide ions. Notice how I keep that polyatomic ion together. And then that reacts to form our iron 2 hydroxide plus 2 sodium ions plus 2 chloride ions. And then remember, when we go from ionic to net ionic, we are then going to eliminate spectator ions. So I can see that I have 2 chloride ions over here, 2 chloride ions over here. I have 2 sodium ions over here, 2 sodium ions over here. And then that is all my spectator ions. So my net ionic equation then will be my iron 2 plus ion plus the 2 hydroxide ions react to form iron 2 hydroxide. So this is the same thing that we were doing at the beginning of this lecture. However, we're just adding one more layer of looking at what is soluble and what is insoluble. And that's it. All right. So you have some practice problems on this stuff. Let me know if you guys have any questions, and good luck.